What I'm going to talk to you today is about developing groundwater for a resilient future. And I'm going to draw on examples from Africa and Asia. So as head of groundwater at BGS, we have projects all over the world. So about a third of our work is international, and maybe about 2/3 is in the UK. So we've got projects, this map shows the projects we've got in about 20 different countries. But you'll see that there's a focus in Africa and South Asia. So really I want to take us through a talk of a tale of two groundwaters, focusing on Africa to start off with, and then looking to South Asia. So Africa, where groundwater isn't extensively exploited, and there's lots of potential for its exploitation, and in northern India, Pakistan, where groundwater is already heavily exploited, with lots of narratives of overexploitation and depletion. So how I'm going to structure the talk today is, first of all, start off with Africa, and I've worked there since about 1995, doing projects there, and then I'll talk about South Asia, where I've been working more recently, just probably in the last 10 years, where I've been working more extensively in South Asia. So in Africa, we'll start off with a continental view, and then I'll do a deviation into work on the crystalline basement aquifers, and then zoom right into individual water security. So look at individual supplies, particularly hand pumps, and what defines people's water security there. And then, if there's time left at the end, I'll go to South Asia and look at where groundwater is extensively exploited. So first of all, let's start off in sub-Saharan Africa. So Africa, south of the Sahara. So here I thought I'd give you some data from the joint monitoring program from UNICEF and WHO to show the access to safe and reliable water supply. So the dark blue is safely managed water. That's water that's piped to people's individual houses. And you'll see that the coverage of that is about 30%, 32%. Basic water supply is water that's available within 30 minutes walk of somebody's house. And you'll see that then coverage increases there to about 2/3 of the continent. People have access to either safely managed or basic water supply. And then the three at the top are those where people don't really have access to a safe water supply. Limited means there is maybe an improved water source within an hour, but then unimproved and surface water, as what they say. So you'll see a third of the people across sub-Saharan Africa do not have access to an improved water supply. So the question here really is, how can groundwater be used to improve water security and therefore help deliver all the sustainable development goals and reduce poverty? That's the kind of question that we've set ourselves here. I thought I would give some examples of what happens when people do not have access to improved water supply. And this is from some work that we did in several years, both in West Africa and then latterly in Ethiopia, looking at the impact of lack of water on people's livelihoods. So the first picture on the top left there is really to illustrate the waterborne diseases. So waterborne diseases are still a major issue, still a high rate of mortality due to waterborne diseases. The second one there is really emphasizing the amount of school days that are lost by children collecting water, so people having to go and collect water from quite far afield. And then the bottom left is a sort of example of how education, is how it affects the economics, particularly for women. So they're spending a lot of time collecting water and therefore not able to be more economically active. And the bottom right one there just illustrates how a lot of the burden does fall on women. So this all means that access to water is not just about water. It's about the Sustainable Development Goals. It's about food, it's about economic activity, it's about equity, it's about education. So just to remind us how important access to water is. And I thought I'd just put in a graph of some work we had done during one of the last severe droughts in the Horn of Africa, where we looked at people's access to any sort of water. So this is not improved water. This is any water that somebody could get access to. And this was in villages that didn't really have a borehole. They didn't have access to an improved source. So it was access just to whatever water they had. And you can see that during the droughts, so the red El Nino droughts, you see that people were taking maybe more than 10 hours sometimes to collect water. So you can see people were completely consumed, their whole time was consumed with collecting water. But if you go back along that graph, you'll see that even in the dry season, many people were taking more than 3 hours, maybe 5 hours of their day collecting water during a typical dry season. And only in the wet season, where time's less than maybe an hour for people to collect water. But the other side of that axis shows how much water people were collecting. This is per person. And you can see that even in the wet season, it might even be just 15 litres per person per day, which is pretty low and below the basic standards that people should be collecting. And then during the dry season and drought, you're getting down to less than 5 litres a day, which is below the WHO sort of minimum limits of survival. So access to clean water, access to reliable water is still a major issue for many people across the continent, and you still have probably 350 million people without access to a safe and reliable water supply. So this is still an issue that is very live and ongoing for people. So as a hydrogeologist, this then gives us the question, or gives rise to these 3 questions about how groundwater can help with this situation. Firstly, is there groundwater available? If there's no access to water, is there groundwater there? Second question, if it is there, how sustainable is it? How long will it last? And lastly, will it be safe to drink? So I'm going to give some examples of answering these questions from a kind of continental scale, and then we'll get down to kind of village scale in a few minutes. So looking at these kind of questions, is groundwater available and how sustainable is it? So for the last 15 years or so, we've been developing these continental-wide maps to try and answer some of these questions. Developing quantitative maps to work out how much groundwater storage is there, how much water can be extracted, looking at groundwater recharge, so groundwater recharge down here, and then doing other maps such as how much groundwater has been depleted or accreted, and what the water quality is, what the salinity is. And lastly, this one down in the bottom right, using that kind of hydrogeological data to give kind of sort of more derived maps, such as what's the potential for solar energy across the continent for pumping for groundwater. So these kind of maps has really helped us inform kind of discussions of water security at a high level. So these maps are generally for discussions with the World Bank, with the African Ministers' Council for Water and such like, to look at what is the potential across the continent for groundwater to answer some of these issues about access to. So I thought I'd give you just kind of one example, and that's about water security metrics. So sort of conventional water security metrics for Africa would be like the one I've shown there on the left. And basically, it's showing that the continent is extremely water insecure. So there's hardly any water in Northern Africa or in Southern Africa, and even in the middle, you've got lots of months without much water. So it's a very insecure water continent, or continent. And you'll see that a lot of these metrics really just follow the rainfall pattern. So the map on the right there is just a rainfall map, and it shows the amount of rainfall that's occurring, and these metrics tend to go together because the water security metrics are really how much sustainable, how much renewable water people can take. Now, I can argue, maybe controversially, that this misses possibly one of the biggest aspects of this story, which is the groundwater storage. Because what you find in some of these countries that are supposedly very water insecure, they're actually still got water supply, they're still being able to use water, they're still developing water, and by adding in groundwater storage, you find that these countries seem to be a lot more water secure. So I think by adding groundwater in, it really, really helps. So what I've done here simply is put 2 of these maps together. The groundwater storage map, need to put my glasses back on to read it. The groundwater storage map up the left, and then the long-term groundwater recharge map along the right. So I have these two kind of axes, and by putting these maps together and doing the kind of metrics together, you can see which countries have got lots of recharge. So ones that are sort of light blue. I'll try the pointer again. Oh, I think it's. So for example, these areas here, lots of recharge but not much storage. Or thinking of the Nubian aquifers and other aquifers in North Africa, fairly little recharge, but actually lots of groundwater storage. And if you look at the whole continent, you find there's actually very few countries that have both low recharge and low storage. It's quite interesting, and I've ranked them, these kind of these histograms I've shown either side there. I've kind of ranked them according to recharge and storage. And if you have time to look at that in detail, you'll find that most countries either have a lot of groundwater storage or are recharged regularly every year. So you only have these kind of 5 countries that have problems with both of them, and some of them quite small, Eswatini and Lesotho being quite small. So I think it's just quite an interesting way to begin to think about water security at this continental scale and see that the role that groundwater storage has in actually helping improve water security. And it opens up all sorts of discussions then about economic and social and ethical discussions about should you be depleting groundwater resources or not. But I'm going to leave them aside for now. I think it's just useful to see what storage is there. So how can that storage and that and the permeability of the groundwater, how can that groundwater be used and then developed for increased water security? So I've split up the continent here into kind of 4 very broad types of hydrogeology. So volcanic rocks, a very small component, but very important in the Horn of Africa. You think of sedimentary rocks, we've got the big sedimentary basins of the continent. We've got unconsolidated sedimentary basins too. And then the bottom right, basement rocks, which are 34% of the continent, but actually 40% of sub-Saharan Africa, and actually where most people live. So if you look at where the basement aquifers are, that's actually where most people are actually living. So it's a very, very important aquifer for water security across the African continent. So I'm just going to discuss a little bit more about the basement aquifer. So the basement aquifer has been pretty successful on providing water for hand pumps. So there's been hand pump programs across the continent being able to develop groundwater from basement. But with the Sustainable Development Goals that wants to push towards increased access to water at the household level, and also for food security, then need to think beyond hand pumps for the basement rocks. So the question is, can these basement aquifers support a higher yield than a hand pump? And can we actually predict slightly better the yield you'll get from drilling a borehole into basement aquifers? And then lastly, can we use that information to systematically map these aquifers better and therefore help target some of the interventions? So I'll talk through the crystalline basement aquifer a little bit here. This is the kind of conventional model of what the aquifer is like. So it's ancient rocks, Precambrian rocks mainly, that got no primary porosity or permeability. It relies very much on weathering. So the regolith on top is where the aquifer has been weathered, and it relies on fractures. And there's been many authors over the decades developing that conceptual model of how these aquifers work in terms of the regolith and in terms of the fractures. And this kind of graph on the right shows the conventional thinking of how permeability, so this graph here, how that varies with depth. So you see that permeability can be quite high in the sort of shallow soils. You might have a tropical soil, like in a laterite or something, quite high there. But then during the weathered zone, where you maybe get some clays and sands, permeability tends to reduce while the porosity increases because it's more intergranular. And then when you get to the base of that kind of soft kind of regolith, you get into more coherent rock that is fractured and more open. And there the permeability jumps, and you get high permeability in this area where the storage reduces. And then when you get into the fresh rock below, you generally are quite low in terms of permeability, apart from if you've hit a vertical fracture zone, a tectonic fracture, where you might get a very high yield. So this kind of general pattern of the kind of weathered basement rock has stood us in very good stead for developing the aquifer for hand pumps. You can use geophysical methods to see where the weathering's a bit thicker. You can drill boreholes that then target that kind of lower high permeability zone. And even in some areas, you can do hand-dug wells, which it kind of gives some sustainability, although they can be quite dodgy. So that's kind of general weathered basement aquifer model. So we've used that then to develop a numerical model and a stochastic model and a numerical model together to try and work out what kind of yields you will get from crystalline basement rock. Can you get more than you get for a hand pump? So what we've done is use that generalized model over here. We've got stochastic representations of thickness of the regolith and the permeability from data this was from northern Ghana. Built a model, run lots of Monte Carlo simulations, and then get predicted yields and then calibrated them. I think the red ones are the calibration and the black's a model, calibrated against the data. So that kind of work has shown us these two important factors down the bottom. First one is, what's the really important things that are driving permeability in these basement rocks that are so important for water security? Well, the first is the maximum permeability at the base of that sap rock. Second is the thickness of the regolith. And then for some larger yields, so if you're looking to go larger than a hand pump, it's things like the water table depth, the aquifer extent, and the recharge. So that's been quite useful, just helping us understand what is it that drives the permeability. And then the bottom right here then shows us, for this bit in northern Ghana, how much water you could get out of the basement rocks. So just for context, a hand pump is about 0.2 litres a second. I don't know why I've got the cutoff here as 0.1 litre a second. It should be about 0.2 litres a second is a hand pump. 1 litre a second is for quite a larger supply. So you could get quite a good small village supply from that, reticulated supply or some small-scale irrigation. And you can see that 30% of these boreholes that were drilled for hand pumps could actually do a larger supply within them. But only 1% could do greater than 5 litres a second. Now, 5 litres a second, if you think about Texas, that's nothing, really, is it? But 5 litres a second is what people will be thinking of for a sort of more commercial, the minimum for any kind of commercial irrigation. So you can see these aquifers are not really going to go for larger irrigation, but for the smaller interim irrigation, or maybe small reticulated schemes, that might be okay. So that was the first piece of work we did on basement rocks. The second one was to recognize that basement rocks are complex, varied, and they're not all the same. So this kind of picture here is to show all the different types of basement rocks we got. As hydrogeologists, we tended to lump them all together. Lump the gneisses in with the granites and the metasediments. But let's actually think about these as different and see if we can predict yields better by doing that. So what we've done is then trying to see, can we look at differences between areas? So we widened our research to across the whole of West Africa, and we split it into different kind of zones or typologies, and then found case studies within it where we had information on the depth of the regolith, or the permeability, and then we had data to calibrate it with. So we looked at this kind of wider area and see, can we spot differences in yields of wells between these different types of basements? And the short answer is yes, we did. So that was quite good. So by mapping the kind of hydrogeology a little bit more detail, we could find differences between different types of typologies. So press the wrong button there. Press the wrong button again. That one. So these are the different typologies. Sorry, I haven't tidied up the names of them here. So just say these are different typologies represented across West Africa. And across here is a probability of getting a borehole of a certain yield. So, for example, this kind of cyan blue is 1 to 5 litres a second. So for this typology, you can see there's a 20% possibility of getting a yield between 1 and 5 litres a second. So you can see that there's significant regional differences between basement rocks on how much water you can get out. And across the piece, it was still about 25% could sustain this kind of larger yield of 1 litres a second. But you can see that for several of the typologies, there's more of this kind of dark blue here. And actually, you could have a higher yield of maybe 5 litres a second or more in some of these typologies. So you can see that it actually has been possible to map these in slightly more detail. So that then led us to, is to develop a map with lots of others and partners in West Africa to do a new kind of hydrogeological map for the ECOWAS region of West Africa, where we could split up the basement rocks instead of them just being one colour. I mean, if there's any hydrogeologists here, basement rocks used to just to be brown in hydrogeology maps, which meant no significant aquifer. What we're trying to do is split that up and see, how much water you can actually get out of these different aquifers. So we managed to publish this map and just help understand how much yield you can get out of them. So the third thing we wanted to do with basement aquifers then is, we've gone from Ghana to West Africa. Can we do it for the whole of the continent? Will there actually be ways of doing that? So we've got some really good geologists involved in that to try and see, could we think of a generalized model for how to generate an aquifer in basement rocks based on the left there, based on the potential for increased regolith thickness. So that might be to do with the slopes, it's to do with the climate, to do with rifting. And then the bottom part of that is looking at domains, looking at the type of rocks we've got there and the potential for fracturing. So we split the whole of the continent into these kind of provinces and domains, got lots of data sets for them from within these countries, working with lots of partners, and then have developed this kind of Africa-wide map now of crystalline basement rocks and the potential for groundwater for it. So this is kind of pretty fresh off the press. It's paper not actually submitted. It's just in the final preparation. I haven't quite managed to get it all together yet. But we've split up the whole continent into these different domains, and then we've got different basement yields for them. So what we hope with this information then, it'll be possible to be able to plan and target a little bit better where you can have higher water supplies than just a hand pump, where you could maybe have solar pumps that can pump and be reticulated around a village, or the very few areas where you might be able to develop basement rocks for a town supply, or some more supply than that. So this kind of information and this approach seems to be working quite well across the whole continent. So that was a bit of a deviation into basement rocks, and the reason for that is it's just so extensive across sub-Saharan Africa, and so many people live on basement rocks. But just want to spend a few minutes then zooming in now into individuals' water security. So what is it that somebody living in a community or a village, what determines their individual water security? And this is part of work that we developed between 2015 to 2021. We had this grant to look across 3 countries, in Ethiopia, Uganda, and Malawi, with lots of good partners, to look at this issue of the functionality of water points. Because what really determines somebody's water security is having access to a functioning water supply. And that's the important word, a functioning water supply. And if I was with my students here, I would be asking them, how do you define a functioning water supply? And actually, you can answer that within 3 seconds. You can say, it's a water supply that works or not. But then when you think of it for more than about 10 seconds, you think, well, actually, what do we mean by working? Is it one that is giving its design yield? Is it one that is working every day of the year, or one that's working more than 11 months of the year? So actually it gets a little bit complicated to begin to define what a functioning water supply is. So for our work exploring this across 3 countries, we had this definition of a functioning water supply. So sorry, it'll take a little bit of time just to talk through this slide, but it's important for looking at the stuff that comes next. So what we did was we followed this flow chart. So first, if a water point is functional, is answering that first question: is it flowing or not? Is there any water flowing out of the water supply? So that's what we'd call a kind of basic functionality. The second one is there sufficient quantity coming out of that hand pump? So if that hand pump had been made for 250 people and a yield of 0.2 litres a second, is the water point actually giving that? And then the rest of the slide there shows about its reliability. And we chose a kind of quite a lenient one. Is a water supply working for at least 11 months in a year as a kind of reliability index? So what we have here then is a range from fully functional, if it is giving the right yield and is fully functional for 11 months of the year, right down to the bottom here where it's been abandoned. So we have this kind of different kind of indices for a water point being functional or not. So what we did is we surveyed this across Ethiopia, Uganda, and Malawi. We had a really good statistician to help us develop a program there that was indicative for the whole country. And then we rolled that out. So I just want to go to the results of that survey. So for Ethiopia, that first index of is there any water flowing out of the well or not? So you go to a well, is there water flowing out or not? What we found for Ethiopia was that for 82% of the sites across our survey, there was water flowing out the well, so it would have been functional according to a lot of surveys. Now, this was a great number because this was exactly the same number as the Ethiopian government had got from after spending a year visiting as many water points as they could. So with our little targeted survey, with the help of a statistician, we got the same number of them as basic water supply is 82%. That's a good number. You think, well, they're doing really well. That's excellent. But then when we began to delve into it more deeply and ask the question, are these water sources giving the amount of water they're meant to be giving, which isn't a lot, it was maybe 0.15 litres a second, we found that functionality rate dropped to 59%. So that doesn't sound quite so clever. And then when we looked at the reliability, we found that it went down to 45%. So only 45% of the the hand pump boreholes were giving water of the right amount throughout the whole year. And then if you added in water quality, it reduced to 28%. So I'm generally quite an optimistic person, and I like to think how groundwater is really good at solving lots of problems. But this information and data, I think, are really important for helping highlight where some of these water points are not working correctly, and therefore how can we actually intervene and help advise on making them more sustainable. Because these individuals are now suffering more water insecurity because their water points aren't giving what they should be doing. So what we then did was we went to 150 water points and we deconstructed them. So we spent about a year in each country with teams, well, about 9 months in each country. We went to about 50 water points in each country. It took about 2 or 3 days per water point. We completely deconstructed them and then worked out what was going wrong or not. So we deconstructed the pump to look for things like corrosion or defects. Looked at the material and the construction. And just to say, we did actually provide an alternative water supply while doing this, so it's not as if the communities had no water while we're doing this. So we provided lots of alternative water supplies for them. Then we did pumping tests, so we looked at the aquifer properties. So we looked to see what was the permeability of these boreholes. We looked at the water levels. Then we looked at the water chemistry of each of these water points, and actually looked at the residence time. So we're trying to work out the age of the water as well. So, because one of the questions might be that some of these water points aren't functional because there's no recharge and they're running out of water. So we wanted to answer that question. So we looked at water quality here, and then we looked at residence times. And I tend to use dissolved anthropogenic gases, chlorofluorocarbon and sulfur-fluorohexate, to work out these kind of questions as well. So we looked at that, and then we did a good old-fashioned borehole camera, just have a look around the borehole and see what's happened to the casing, and is there any problems down there? And at the same time as we did that, we had a social science team going out doing lots of focus studies with the communities, trying to piece together the kind of breakdown history of each borehole when it had broken down, and then what the impacts were when it did break down, what happened, where did people get their water, and then really try to get under the skin of how people manage their water points. When it broke down, what did they really do to get it fixed? And then we in place some sort of community researchers in a subset of communities to keep diaries on what was happening over the following year. So quite a lot of work there just trying to understand what's happening in an individual's water point. So I've just got to rapidly give you the results because I'll need to get onto the Indo-Gangetic Basin for the last few minutes. So just sort of the highlights from these kind of detailed, intensive studies, and we've published most of this. So the first one is that most of these rural water supplies, in fact, every one that we looked at were actively being recharged. So it's not like recharge had stopped for these aquifers. They were being recharged every year. They were getting water supplies and they were recovering. The second issue we found was that corrosion was ubiquitous. Every water point we looked at, just about, there was some issue with corrosion of the materials down the well, and this was probably that was driving a lot of the poor functionality. So we've got another project now looking into the kind of materials that people are using and such like to try and answer more of that questions. The next bit we looked at was the aquifer properties, and we found that actually quite a lot of these boreholes were sited where the aquifer wasn't permeable enough for people to get enough yield even for a hand pump. So maybe there's questions there about, are they using the right methods to site? Could they spend a bit more money on some geophysics or some hydrogeologists or geophysicists to help them site the boreholes? And then we looked at the rising main, so that's the pipes inside the boreholes. Most of the ones we looked at were substandard. They weren't thick enough, which is where that red line is. And one that surprised me, because I wasn't expecting it, was that the water levels were quite deep in places. So normally I've kind of, up until this point, I thought water levels are generally shallow enough for a hand pump, generally maybe 10, 20 meters deep. But we're finding water levels maybe at 40 meters deep, a lot deeper. And the reason for that was competition with things like flower farms or more commercial use of water. So that was the results of the kind of physical studies. And then with the social studies, we found sort of three things to share with you here. One was people were rarely using the management structures created for the water point to manage the water point. So when the water point was put in, there had been a water management committee set up with 6 men, 6 women, a bank account. They were rarely being used. What happened is people tend to manage it in their own way, be it through a church group or a mosque, be it through a growers consortium. So people were using these kind of institutions, and I think for the WaterAid and other NGOs and charities we're working with, maybe supercharging some of these existing structures is probably the thing to do. Second thing was really, and this was widespread, was a challenge of getting support to fix things when they went wrong badly. So people could maybe fix it if a washer went wrong, but if they needed a big change, there wasn't really that support to do it there. And this was across the piece in Malawi, Ethiopia, and Uganda. So here's something that can be done to try and improve that kind of support, either through the private sector or through government or in other ways. And lastly, what we found through the diaries was that a lot of these communities were under immense cascading pressures of demand. So every week, it seemed in a lot of communities, there would be an event, be it a funeral, be it something else happening where you'd have 1,000 people trying to use a water point rather than 200. So you had this huge, massive increase in demand. And then once one water point failed, people come from another village to go to another one. So you had this huge kind of demand and this kind of cascading pressures. And then things went round down like dominoes. Once you've got 1,000 people using your water point, it would begin to fail. So again, these are all things that can be worked in, can be managed, can help inform new kind of water programs. So just to kind of summarize the kind of this run through Africa and a kind of overview of the opportunity that groundwater has to meet some of the water demands there and try to help towards economic growth and poverty reduction. I mean, first of all, hopefully you've got the message. Groundwater really is fundamental to water security. It's not big reservoirs or big water transfers. It's local groundwater that is really going to be the main answer to help for water security. And also, the groundwater resources are generally available. You know, you need to look for them. You need to have good people to be able to find them within a community. But generally, in most environments, there's enough there for a hand pump and maybe a little bit more for a solar pump, for example. I'd argue there still needs to be massive investment in kind of basic services to meet that kind of access gap at the moment. And we need to make sure we're keeping pressure on the World Bank and such like to make, or whoever's got the money, to make that money available to help get these basic services. And then I think there needs to be more effort, and this is speaking to geologists and hydrogeologists, there's a lot of work we need to do to conceptualize the groundwater systems and help improve sort of simple siting methods. How do we get boreholes in the right place? How do we understand what's going on in the groundwater here? There's a lot more we can do to try and help that process and work with our partners and colleagues across the continent. Then lastly, that kind of final point about functionality. A big effort to help continued functionality of these water points and how they're managed and how they're repaired when they go wrong. These are the things that people need to focus on. So for the last few minutes, I'm going to talk a little bit about South Asia. I think I had 45 minutes, is that right, Bridget? So, all right, okay. I'll have to take a drink of water then. Sorry, can you all hear my accent okay? It's quite a strong Scottish accent, so apologies for those who are not used to a Scottish accent. So moving away from the kind of opportunities of Africa, then it's just looking at some of the work we've been doing with partners in South Asia, so where it's maybe the other end of the spectrum. So I'm going to concentrate on probably arguably the most productive aquifer in the world. Maybe that's a little bit contentious. One of the most productive aquifers in the world, 250 million, it's 250 cubic kilometers a year, so quite a lot of water. So this is where it is. It's made up of the Indus River and the floodplains associated with it, and the Ganges River, and then you've got the Brahmaputra coming around the back here. So the low-lying ground associated with the floodplains of the Indus and the Ganges and parts of that Brahmaputra. So what's going on here? What's pressurizing this really important aquifer? Well, first of all, direct climate change effects, the sort of increase in temperature, changes in the Indian monsoon. Also, the melting of the glaciers. You know, all these rivers, but particularly the Indus, is focused on, is fed by melting glaciers, and they're changing. There's also the dams and canals. This area has got a huge amount of canal network across the whole of it, and that has a huge impact. Increased demand as we go to triple cropping for a lot of this area, so an increasing demand for groundwater. For things like sugary drinks, this is a Scottish sugary drink called Iron Brew, but anyway, sugar, cotton, rice, of course, all very important food stocks across the Indo-Gangetic Basin. And then, of course, this narrative of depletion, and this is from the Grey Satellites, one of the first pieces of work with the Grey Satellites by Matt Riddell and his team, showing this depletion across northwest India. And we have about 11 million tube wells in this aquifer. So, for me coming from Scotland, that's a lot of boreholes, but you've got a lot of boreholes in the US as well. So lots of people abstracting groundwater. So what we've been doing in this part of the world, this is a map of projects we've been doing over the last 5 years. We've been looking at lots of different angles of the system, looking at the groundwater, the typologies, and looking at groundwater surface interaction. So I'll talk you through a few of the kind of summaries from some of these projects that just tell us a little bit about this very highly exploited groundwater system. So the Indo-Gangetic Basin, this is a kind of map of the hydrogeology Indo-Gangetic Basin. If you look at hydrogeology maps, generally, they would just have this as one color, blue, an unconsolidated sedimentary aquifer. But there's a lot of variability within it. And so the groundwater storage is very high. It's about 30,000 cubic kilometers. And that's important because about 20 times the annual flow in these huge rivers of the Ganges and the Brahmaputra. It's also about 100 times the storage, the dam storage of the Ganges and the Indus. So large storage. Also very different from the basement aquifers in Africa is that you can pull out 20 litres a second without even thinking about it. You can drill a borehole in many parts of these places and get a lot of water out. So very easy to exploit. But there's also very large variations in the aquifer typologies, in the permeability, in the storage, in the kind of layering, the anisotropy of the aquifer. So although it's all unconsolidated sediments, there's a huge variability across this aquifer. So that's the aquifer we're talking about here. So what's happening with the status of groundwater? So again, as I said in the last slide, this was one of the first areas where GRACE really got to very prominent global media coverage, when it showed this kind of bullet hole in northwest India and Pakistan that showed this groundwater depletion. So using the GRACE satellites to look at total water storage, and most of that associated with groundwater. And this was done at the same time by an Indian scientist, Dr. Tiwari. So the satellites showed that there was big depleting groundwater. People kind of knew it anyway, but this got to real public attention, and to the ministers in India particularly, that something had to be done about it. So we decided that we would take that opportunity to look at the in situ data for groundwater levels. So not just looking at this kind of satellite data, but could we actually get lots of in situ data to see how groundwater levels were varying? And what we found that you got a much more complicated situation about groundwater levels. You'll see that the depletion, which is the bright red, is happening, but it's much more localized. And you're actually getting rising groundwater levels, which is the bright green, right next to the depletion. So it wasn't all depleting. Quite a lot of it, groundwater levels were rising. And as you went further down the basin, then there was much less depletion going on, apart from a little bit round about Dakar. So you had this sort of variation in kind of spatial coverage of depletion. It was quite a nuanced picture. And then we looked at we'd managed to find a few boreholes that had over 100 years worth of records. And so we've got the depletion happening that GRACE could show us, from 2000 to this, I think this was only 2010. You could find that depletion. But when we looked at these long records, we found that actually the story for the 100 years before that was groundwater increasing. So actually, the groundwater resources here had actually been increasing according to these 4 wells for the previous 100 years. So not only was there a big nuance spatially, there was also temporally when you looked at this kind of longer time frame. And also, I'll just run through a few slides here, but it's important to mention when thinking about this aquifer, there's a lot of issues with water quality as well, to do with arsenic and salinity. So and that's a very important aspect of this aquifer. And we found that by splitting up this aquifer into 3-dimensional typologies, you could begin to understand why some of these depletions and accumulations, why this was all happening. So looking at it in a 3D sense really helped. Anyway, these 4 wells that showed that kind of increase in groundwater storage for the previous 100 years kind of piqued our interest. So we went back with a project where we managed to digitize about 4,000 hydrographs. So that was going to lots of old paper records with our partners in NIH Roorkee and also in Pakistan. And we got together the 4,000 records and we pieced them together along with records of when canals had been constructed, and also when tube wells had been installed. And we pieced together all that information and put that together an analysis to look at 150 years of change in this aquifer. And I'll just talk you through this slide, and then I'll probably be just about finished. So the first thing to look at here is, well, I think at the bottom, this is about 1900 to about 2010, I think is where our data stopped here. First thing is to look at the groundwater storage from these hydrographs. And you can see that groundwater storage accumulated from a low level in the early 1900s, accumulated till about 1960, where it then kind of stabilized and then started to decrease in about 1990 is when we got this more recent depletion. So the biggest story of this aquifer over the last 150 years is one of groundwater accumulation, not of depletion. So the big story is about groundwater resources accumulating. And the second thing then to look at is to look at the relative precipitation. So this is red means there's less rainfall in that decade than the historic average. And you could see that the groundwater was accumulating in times where precipitation was actually historically quite low. So it wasn't due to the precipitation here, there was another factor at play. And what that factor really was the construction of these canals. So this is a cumulative construction of canals. The darker colors are decades where they constructed an awful lot of canals. And you can see that the huge increase of canals in the 1950s onwards coincides with the accumulation of groundwater. So what was happening here was these canals, 100,000 kilometers of canals being constructed in the 19th and 20th century. This was spreading out surface water across this aquifer, which was leaking into the groundwater system and making groundwater levels rise. And it was only more recently that the increase in boreholes then began to deplete the aquifer. And there's also other nuance in here is that actually the increased precipitation during this period, the latter half of the 20th century, mitigated a little bit of some of the wells going in. So actually there was increased recharge at this period. So the big story here was finding that groundwater is accumulating and that these canal networks act as a massive managed aquifer recharge system. And I think you've found similar things, or Bridget's found similar things here in the US in some of the large irrigation systems. So I'm going to skip through some other work that we're just about to publish, which goes into this in a little bit more detail, just quantifies effects from canals and rivers. So we're just trying to work out how much comes from each now. So we've just about finished that. And then I've got some slides that show a little bit about delving into the actual relationship between the canals and the groundwater and how it changes in some areas using stable isotopes. But I've run out of time. I think I spent too much time getting excited talking about Africa. But a lot of the stuff is written up in different places. So a summary then for the Indo-Gangetic Basin aquifer, at the different end of the scale to the basement aquifers in Africa. See, it's already been an aquifer that has been brilliant at buffering climate variability. So farmers have been using it to buffer climate variability, and it's extensively developed. Depletion is certainly happening, and it's is a real problem in some places, but it's spatially complex because you're getting this recharge as well from managed from the canal network. This is an aquifer that's not just been changing for the last 20 years since Grace has been around. It has been changing and developing for 150 years, and even longer before that, where there's been sort of historical canals before that. The aquifer properties of this aquifer really vary very much spatially, and actually the way you govern or manage or remediate this aquifer needs to change according to different parts of the aquifer because of the aquifer properties. So I haven't really spelled that out, but it's an important factor in trying to remediate the aquifer. And also, groundwater quality is arguably a bit more important here than depletion. We talk about depletion a lot for this aquifer, but the arsenic and the salinity is arguably a bigger management issue that should be looked at. And really, human-induced groundwater accumulation is a large part of this storage. And that gives quite a bit of optimism here, because we can see that humans have been impacting this aquifer, and there's maybe ways that they can be remediated using some of these processes. So I hope you've stayed with me as I've gone through the kind of tale of two groundwaters, the kind of potential for groundwater development across much of the African continent, and then also to manage groundwater resources in the kind of very heavily exploited Indo-Gangetic Basin. And what the common thread between these two is the importance of understanding the geology and the hydrogeology and the processes that then help us be able to tease out how the opportunities arise and how management can be most effective. So, thanks very much.
Thank you so much. That was such an amazing and educative and enlightening presentation.
Thank you.
So I have a question. I'm not a groundwater expert yet, but I do know that, at least to some extent, geophysical and hydrocarbon exploration or seismic exploration can in some way affect the permeability or porosity of the aquifer. So in those areas or those countries that, I'm talking about Africa now, in those countries that you deconstructed and looked at the aquifer characteristics, were they close to areas of geophysical or hydrocarbon exploration? I'm asking this question because I'm from Nigeria, and the part of Nigeria I come from, there's lots heavily hydrocarbon exploration, and this has affected the water recharge, quality and all whatnot for the past couple of years. So I'm just curious about that.
Oh, thanks for your question. That's I lived in southern Nigeria for 3 years and did a lot of groundwater work just above the delta. So I hear where you're coming from, and I think in my experience of groundwater, particularly in West Africa with hydrocarbons, one of the main issues for it has been contamination. It's been more about the kind of hydrocarbon, the way the hydrocarbons has been developed, that they contaminated the aquifers, rather than direct kind of damage to the aquifer system themselves. It's more to do with the water quality aspects of it. I mean, what can happen to an aquifer, an unconsolidated aquifer, is if you deplete it very, a lot, then you can get some consolidation and some reduction in the permeability in it. But in most of the places I've worked, particularly in Africa, that's not been a major consideration. It's mainly been the contamination.
Thanks a lot, Alan. I was forgetting my question. So, you see a buildup of storage regionally in the Indo-Gangetic, 400 cubic kilometers median value. So what is the net, considering the regional depletion in the last couple of decades? So are we still 300 cubic kilometers up, or, what's the net?
Yeah, it's a good question. The 400 kilometres is very conservative, because that was only in areas where we definitely had data, so we didn't extrapolate away from where we didn't have data. So from our analysis, you'd say the net's about 300 cubic kilometres, but I think it's probably quite a bit more than that, because outside of the areas we didn't have data, we decided not to extrapolate it.
So regionally, there's no depletion then, there's a build-up. And locally, you can have depletion.
So the issue is a distribution of it. So, and accumulation's not always good. So, for example, what's happened in the lower Indus is that a lot of accumulation has happened, and you get saline groundwater. So that kind of rise in groundwater levels has salinized the groundwater. So it's actually it's not all usable. But the very localized depletion in the Punjab, for these areas, it is very real, and you have groundwater levels going down pretty quickly. But just to the south of Punjab, you then have quite high groundwater levels, and you have quite saline groundwater. So you have these two things existing together.
One more question.
Thanks. Very interesting, extensive work in continental scale. And I want to thank you for that. I have actually two questions. One is there like an effort to change this continental scale groundwater modeling in Africa and Asia to maybe a data set or as a benchmark data set so that it can be used in modeling? That's my first question. My second question is about GRACE on the application in Indo-Ganges Basin. So there is an accumulation in the past before GRACE came active. So with that validated with using point data, how can we kind of justify, because GRACE being gridded, covering a huge spatial resolution as compared to wells, so how was that mitigated in the comparison? Thank you.
So, first question, I've forgotten already. What was that? Sorry.
About
my brain.
About a data set.
Data set. So,
yeah.
so on the data set, yes, most of these I've made available online. So in the papers with them, there should be a DOI to the data set, so that they should be available for that. The second question was about comparing the in situ data to GRACE. Was that what it was? So yeah, so we did that for the period where they overlapped, and we got a very good agreement. So when we looked regionally, the agreement was very good. So what's interesting about that, as a little aside, what's interesting about the picture, this one here, is if you look closely at it, the bullseye isn't actually in the Indo-Gangetic Basin. It's just south of it. It's in Rajasthan. So actually, what this was picking up was a lot of the depletion in the Rajasthan desert, which which groundwater level is quite low in. And the bits above it, you can see Punjab and Haryana just on the yellow bit. So when we deconvolved the GRACE signal for these areas that we were looked at, so Punjab and Haryana, there was very close agreement.
I don't think we have more questions. Do we have questions from online? Cool. All right, let's thank Alan again for this very interesting talk.
Thank you.